Now you see two models. They are predator-prey models. And could you tell me the difference between the two population models? Yeah, so if we compare here in both equation systems, the first system of two equations, you have X as predator, Y as prey population, and A, B, C, D, right? Those coefficients, those are positive numbers. Yeah, so they're all positive. So you look at the second system of two equations, and the only difference, yeah, we also have the terms you see, negative AX, BXY, etc., except the additional terms in right. So in the first equation, we have negative, that means minus H1X. So in addition to the terms in common terms, but the difference is that minus H1 minus H2 times the either X or Y. So that is the effect of harvesting. We want to study how harvesting will affect the population growth of predator and prey. So we also assume the harvesting will be proportional to the current level of population. So it will affect the rate of change of the predator in this way, will decrease the population because of this negative times H1. Here, H1 is positive, assuming it's a positive constant. So negative H1 times the current population, that will, as a negative effect, that means it will decrease the population of predator. And similarly, the harvesting of prey, right? By introducing such a term, it shows the harvesting on prey. So here H2 is another positive number. So in addition to the ABCD positive constants, here H1, H2 are also positive constants. As you recall that our constant solutions for this system, for the first system, if we only determine the constant solutions, X equals 0, Y equals 0, that's one constant solution, right? Another constant solution is X is C over D, Y is A over B. So we have two constant solutions for the first model. For the second model, because of the introduction of the harvesting, let's rewrite the second. So we can, everything will be the same, but we can just simply put the X terms together. You see A plus H1 X. It's B XY. So the second equation is same as C minus H2 y minus D xy. So that is the new system which considers harvesting. So this is a new model that considers harvesting on the predator and prey. Has actually similar form. So you just look at this equation and that equation. It's just the only difference is you see this coefficient a becomes now a plus h1, right? So the c is now c minus h2. So for the new system, we can quickly apply the formula. We can still find the constant solutions. As we already know either trivial solution or solution like this. So we can simply write constant solutions for the second system. We still have either a trivial solution or another constant solution, which is this is now C over D, right? Now C is a different value. C minus H2 over D. And the Y will be A over B. A is also a different value, A plus H1 over B. Over B. So now we can see the effect of the harvesting. That means the predator population is smaller than before because of the harvesting. So if we circle this compared to C over D, right, due to the harvesting, so the predator population will be less than without harvesting. And prey population, A plus H1 over B compared to A over B. So the prey population will be higher than before, will be higher than without harvesting. So that means the harvesting will decrease the population of the predator, but increase the population of prey. So we compare that's also for the non-constant solutions, since we know this quantity is actually the average, right? For if you have a periodic solution, and the average of a periodic solution will be this constant. So that means the average predator population will be this quantity, which is less than the average when there's no harvesting, and this one. So the prey population, the average will, if you have a periodic solution, so then the average of the prey population will be this one, which is higher than the average when there's no harvesting. So this explains the actually Lotka-Volterra system and also the harvesting effect for that story. Right, Volterra's model explains why the harvesting will decrease the population of predator, pre-war and after war. Yeah, because pre-war and after war, and yeah, people do the intensive fishing. So then that means we need to use the second model, so that before the war or the war one and after the war, and people have the intensive fishing, so the predator population is less. But during the war period, and this term does not exist, so the population of the predator is close to its natural state. So pre-war, after war, intensive fishing doesn't do good to the predator, but it actually increases the prey population. A similar story. So now if I talk about another situation, you can understand it easily. So this one, we can apply Volterra's law of harvesting to explain this phenomenon. So here is oh, need to pay. So here's Volterra's law of harvesting. We see this law actually can very well explain another phenomenon, that is DDT, which is insecticide. That means it kills insects. Or some bugs. So for American citrus orchards, and there is a particular insect which is called cushion scale insect. So yeah, you don't have to know the name of that, but anyway, it is to protect the orchards from being harmed by that insect. So then people wanted to introduce DDT to kill that insect. So so therefore they introduced the DDT. However, when the DDT was first introduced, then they discovered that they see more insects. Actually, the insects that can do harm to the orchards actually are not decreased. The population of insects is not decreased. On the other hand, it is increased. What is the problem? The problem is because there's a bug that is called okay, so there's a actually there's a ladybug. Yeah, so I want to see the exact name called ladybird beetle. Yeah, so you see there's an insect called cotton cushion skill insect. Okay, let's make it short, just the insect. And there's a ladybird beetle. So the DDT, when people applied the DDT, which is a poisonous product, the intention of applying DDT is to kill insects. However, they killed ladybird beetles at the same time. But these ladybird beetles, they eat insects. They eat this. So actually, we do see the two populations, right? One is predator, one is prey. Using our notation, the ladybird beetles will be X, the population X. The insects will be the prey population Y. And if we use the population model X prime, Y prime, right? So we have differential equations then to model the population change. So then with this equation, for example, and but when you introduce DDT, that's like a harvesting, right? They will kill without differentiating insects and ladybirds. So they kill both. So that means we have a term that we have to include, which is harvesting. So I'm going to write H1. So that is going to decrease the population of X, which is the ladybird beetles. Also, this harvesting, so when you apply DDT, it's going to decrease the insects. So we know that once you apply DDT, it has the effect of the harvesting. So we apply the Volterra's law of harvesting, we will see the average population of this predator, right? Average population of the predator, which is ladybird beetles who eat insects, that will decrease, and the average population will become this. It will be less, and the insects, if we have some periodic solution, for example, the average of the prey population will increase, will increase, will be higher compared to before you applying DDT. So before you apply DDT, the population of the beetles will be C over D. And the population of the insects will be A over B, only A over B, right? But after you apply DDT, then there's like killing both insects and ladybird beetles. Then the effect is to decrease the ladybird beetles population, but increase the population of the insects. So that is against the purpose. So if you are aware of the Volterra's law of harvesting, then you wouldn't apply DDT in such a situation because it doesn't help. On the contrary, it even increases the population of insects.